So, hello everyone, we restart our discussion on the linear viscoelastic response, and in fact in the last lecture that we had we introduced what exactly is meant as viscoelastic response, and we basically were looking at the viscoelastic response as sum total of elastic as well as viscous response. We also discussed in detail about aging materials. Now, what we now need to do is to talk in detail about what exactly is meant as the linearity of the response. So, if you recollect the discussion that we had, we talked about creep compliance, we talked about stress relaxation, all of them in time domain, and in frequency domain we talked about these parameters: storage modulus, the same stress relaxation as well as the creep compliance in the frequency domain. So, now what we need to clearly understand is how do we even define these functions. Apparently, these functions are defined only for a specific class of mechanical response, and that mechanical response is prescribed in the linear viscoelasticity. The linearity that we see in viscoelastic material can be slightly different compared to the linearity that we are familiar with in elasticity. The reason is, since we explicitly take into account the influence of time, even some of the definitions that we thought as simple, especially for linearity, can become very involved. It can be easily related in the time domain, but in the frequency domain it becomes little more complicated. So, let us first now start looking at what is really called as the linear viscoelastic response. Now, what you see in this picture is two different stress histories, and we need to clearly see how to check for the linearity of response. So, we are going to introduce two important concepts, what is really called as scaling and superposition, right. So, let us keep looking at each of them as we go along. So, right now let us get back to our old definitions. We defined a function called creep compliance, which had two parameters T and sigma. So, that means for any given stress level, for any given T, this function returns what is called as the strain at that particular instant for any applied load given by sigma, right. So, now let us take a look at this first picture, wherein we are applying sigma of sigma naught, and you will immediately understand that at each and every specific points the response is given in this following form. Now, let us apply one more loading, which is given by alpha times sigma naught. Alpha is any scalar, and you are going to see that one can actually write this in this specific way. And in fact, please focus your attention on equation 1, in which we have written clearly that this function creep compliance function is j t comma alpha times sigma naught, and since alpha is a scalar, we just take it out and we write it as alpha times j of t comma sigma naught, and which is what is essentially represented in this figure. Now, since sigma naught is constant and alpha can vary in whatever way we want, one can actually write this in the specific way, and so finally one can define a creep compliance in the following manner: creep compliance function. So, that is nothing but j of t is j of t comma sigma naught divided by sigma naught. So, what is that we have done now? We have eliminated the presence of sigma here within this function, and we are going to divide each and every strain as with respect to the stress that is applied. So, that means this creep compliance function can be written as strain per unit stress. Now, it is not very clear to us whether one can define such function for all the class of response. So, we need to have some restrictions on the class of mechanical response for which such definitions are applicable. So, how do we really check for this scaling? For instance, take a look at this picture. This is the creep data, and you can actually see that there are 3 different types of stress levels that have been applied: sigma naught, sigma 1, sigma 2. This is as a function of time, and you will also notice that this is nothing but epsilon of t. So, that means we get back to our old way of prescribing this creep compliance function. So, j t comma sigma. Now, what we are now going to do is to divide each and every strain of this with the appropriate stress, and so we are going to say that if all these lines fall on one specific segment, then we are going to say that the response of the material is scalable, or we really call it as linear scaling. But on the other hand, if let us say sigma naught and sigma 1 fall on top of each other, whereas sigma 2, that means the strain corresponding to sigma 2 is deviating, you are essentially going to say that there is no linear scaling. So, we need to be also very clear to say that up to a response of sigma 1. So, that means you can take this material as given here, and up to sigma 1 the response of the material is scalable, but beyond it the response of the material is not necessarily scalable. Okay. So, now we will look at various ways of interpreting this scaling, what we define as isochrone. So, what exactly the meaning of isochrone? Iso is same, chrone is time, at the same instant of time. So, now you can actually draw a picture in which you plot sigma on the y axis, epsilon, that is the strain, on the x axis, and you try and plot the isochrone, that is j t comma 1 or j t comma 2 at any instant of time. So, how do we do that? Let us go to the previous graph. So, we basically take a look at, this is your creep compliance. So, this is your strain, this is your strain, this is your strain. So, let us take T 1. So, you are going to get sigma naught, epsilon naught as one pair, similarly sigma 1, epsilon 1 as one pair, and sigma 2, epsilon 2 as another pair, all of them at T 1, and you can always do something like this. Similarly, one can do it for T 2 also. So, when we do that and when we plot this particular line, you are going to see, if you are going to get a straight line the way in which it is seen here, you are going to say that this is the response of the material is linear, or what you really called here as linear isochrone. Now, I need to make a clarification based on the statement that I made in the last lecture. In the last lecture, I very clearly emphasized that one should not plot stress versus strain graph for a viscoelastic material, especially when you are trying to plot the creep and recovery, and we also showed the absurdity of some of the graphs. But here what we are doing is, we are picking one particular time T 1 and we are taking this sigma epsilon pairs and trying to plot those graphs to get the check for the linearity. So, these specific graphs have a special meaning, especially when you want to characterize the linear response of the material. On the other hand, you could, if you are going to have the response of the material as T1 and T2, something like this, you are going to say that this is a non-linear isochrone. There is also one more statement that I need to make here, which will become amply clear as we go to the next set of analysis. The linearity as far as viscoelastic response of the material is concerned does not necessarily mean that the response of the material in the stress strain space has to be a straight line. It so happened that in the manner in which we have defined the linear isochrone, these responses seems to be a straight line, and hence you are calling it as linear isochrone. So, let us not confuse our notion related to linearity as a straight line as far as linear viscoelastic response is concerned, and this will become very clear when we start discuss few concepts in the later portion of the lecture. Now, let us say something about superposition. Now, the definition of superposition can be given in different ways. Few slides down the line we will be talking about the Boltzmann's superposition principle, which is a more precise statement. So, as far as this particular discussion is concerned, what we are going to say is a multi-step history plot, if you can regard it as the superposition of several single step history plots, then you are going to say that one can superpose. So, what is the stress history that you are really looking at? So, let us say that you are applying a stress of the following form. So, this is sigma, this is T, T1 and it keeps going. So, probably you are talking about sigma 1 and sigma 2. So, this difference is sigma 2 minus sigma 1. So, when you apply the stress history of this particular response here, whatever is you can actually see that there is a J T1 sigma 1 plus. So, how do we really write this? So, you are going to have T1 here and T is the running time. So, T minus T1 comma sigma 2 minus sigma 1. So, if I could separately take the response of this and take the response of this and add it up, and if I could get the response as given here, then we are going to say that these responses are superposable. So, what it means is, if I take a stress history like this and if this is the response that I am going to get, for instance this could be the experimental result epsilon versus T, and if it is going to vary like this, and if you could separately do another experiment in which you apply a load only for this particular time, and another one for this particular time of sigma 2 minus sigma 1 and sigma 2, and when you add them together, if you get this particular response, you are going to say that this response is superposable. Okay. So, where are the real applications for this? The real applications for this is to check how to do the loading and the unloading history, and we have seen this in the thought experiment on creep and recovery that we carried out in the earlier discussion. For instance, let us say you are going to apply a load of this specific form in which you apply a sigma naught up to T1 and then after that it is 0. So, what we can do? We can write it as a superposition of a sigma naught that runs forever and a minus sigma naught that starts running from T1. So, when you add them together, you get this correct response. So, now when you write the response of this material like this, so that is sigma naught time J of T, and then here it is going to be minus sigma naught J T minus T1. T1 is the time in which you are going to apply your minus sigma naught, and if you could get a response of this in this particular fashion. So, I could draw a strain response something like this. Okay. So, then if you get exactly the same as the sum here for your actual experimental data, then you are going to say that this is superposable. Now, what is the understanding that you get here? The understanding that you get here is whatever be the recovery that you are, the instantaneous recovery that you are going to get, and whatever is the jump that you are going to get here are identical. It is not necessary in any experimental data to get such kind of a response, but within the experimental variability that one normally encounters, especially when we apply this kind of loading for bituminous mixtures, these things are very useful to select a class of viscoelastic models for our analysis. We also need to understand few things here. I will initiate the discussion here. Later when we are talking about flow number and flow time, these things will become lot more easier. Now, please see that there is a response that is given here in this following way. It is practically not possible to apply such kind of loading during any experimental protocol. Normally always this, it will take some finite time to reach this particular stress level. So, whatever is the time that it takes to apply a load of this specific magnitude is normally called in experimental mechanics as rise time, and this rise time depends on the sophistication of the gadgets that you have got here. Depending on the capacity of the power pack, depending on the sensitivity of the loading electronics that you have got, one can reach, let us say, to 600 kilopascal, let it be the 600 kilopascal. You can reach this loading in 0.05 second, 0.1 second, sometimes even 0.5 second. Since we have discussed earlier that the response of the material depends on the loading history, you are going to see different responses for the same material for the same 600 kilopascal loading based on the loading history to which it has been subjected to, and this is a caution that we should exercise when we interpret the data for this kind of a material. So, let us make this statement very clear. If the response of a viscoelastic material exhibits both, this is the most important thing, scaling and superposition for all stress histories, such response is said to be linear. So, that means when you do a creep and recovery, or when you do a stress relaxation, or when you test the material in frequency domain in oscillatory shear, you need to ensure that the response of the material is scalable and also superposition is valid. If only it meets both the criteria, then only you can say that the response of the material is linear, and only then you can actually use any of the linear viscoelastic model. Tacit in all this observation is the fact that you should also be able to include the variability associated with the experimental data acquisition. For instance, in many of the bituminous mixtures testing, we allow for plus or minus 10% variation in the experimental data that is collected. So, within this plus or minus 10% variation, you should be able to meet the scaling as well as superposition, and only then such response could be modeled as a linear viscoelastic response, and you can use any of the linear viscoelastic material. Okay. And now, to emphasize more on this, as of now we have been only talking in terms of stress histories which are fairly straightforward, stress histories or strain histories in which we just applied something like this. Now, what will really happen if you are going to apply a stress history of this particular form or this particular form? Okay. Any arbitrary stress history can be applied. Now, we need to understand that there is a reason why we adopted this kind of histories, because we could use straightforward rate type model, because there is the stress history is, means if you take a derivative of this it is 0 because the load there is no variation, but if it is going to be an arbitrary history, we need basically an integral kind of a model, which we will discuss in the next slide. But we need to make one statement here clearly. So, this is sigma 1 as a function of time, and this is nothing but k times sigma 1. Similarly, there is sigma 2, and you can actually see that this is k times sigma 1 plus sigma 2. Now, when we are really talking about superposition, so this for the sigma 1 t, if this is epsilon 1 t, and whatever you see here, if you are going to get this as the summation of separately k times epsilon 1 t and epsilon 2 t, then you are going to say that this is superposable. Now, if I show this picture as it is, epsilon versus t, and ask you whether the response of the material is linear or not, most of you will basically say that, oh, it seems to be varying, it is not a straight line. So, the response of the material is non-linear. No, it has nothing to do with the shape of the strain curve in the strain time domain. What it means is, since there is a variability associated with the time, we need to all check for scaling as well as superposition, and only then we can conclude that whether the response of the material is linear or non-linear. Recollect the discussion that we had about isochrones, wherein we drew pictures something like this. So, this is a linear isochrone, this is a isochrone in which the response goes like this. Again, let us not get confused, just because the stress versus strain space, this seems to be non-linear. This is basically because of the manner in which we carried out, we defined our isochrones to be of this particular way. So, if to emphasize once more, you can call the response of the material linear only if it meets scaling and superposition and not anything else, right. So, I have actually written a lot of text here for the benefit of the students, and this is the statement of the Boltzmann's superposition principle. In fact, what we presented here is some arbitrary stress history. So, if you are going to have an arbitrary stress history, and if you really want to model the response of this material, especially within the linear viscoelastic regime, it actually makes sense to use an integral model of expression of this particular type. So, how are we going to do that here? So, let us see that here. Okay. First and foremost thing is, we will take a look at this particular picture. So, we apply sigma of sigma naught, and this is what it is going to be. So, you can apply sigma 1 at this particular time, and this is the response is going to be. So, if you have a step stress, this is the response, and we discussed it here. So, what it means is, if we read it here clearly, and I suggest that all the students, especially at the undergraduate and graduate level, spend some time thinking about this statement very carefully. If stress sigma naught is applied at a time t is equal to 0 to a linearly viscoelastic material, the emphasis is on linearly viscoelastic material, then at a time t is equal to psi 1, sigma 1 is applied, the strain output at any time subsequent to psi 1 is given by the sum of the strains at that time due to the stresses computed as though they were acting separately. So, this is the Boltzmann's superposition principle. So, let us use this to see how we can model the response of the material for any arbitrary stress history. So, let us assume that you are applying a stress history of this particular form. So, now what we are going to do is, we are going to kind of split this into very small delta sigma I that is given here, okay, and for each time step it is going to be given as psi 1, psi 2, psi 3 like this. So, we are going to approximate this stress history that is given here in the following form. So, sigma of t is the summation of delta sigma I, and h is nothing but the Heaviside function that was introduced in the earlier. So, if that is going to be the stress history to which you are going to subject it to, then the strain response epsilon of t is going to be nothing other than, so this is going to be, so if you just take a look at it, so this is going to be delta sigma I h t minus psi I summed for all the steps I is equal to 1 to r. So, it is going to be the creep function that is given here, your creep compliant function given as j t minus psi I h t minus psi I. So, I will not spend time on how one takes this summation to an integral. Elementary calculus book should tell you that. So, basically when we write this in the integral form, this is the expression that you are going to get. Now, epsilon of t is integral 0 to t j t minus psi d sigma psi by d psi times d psi. So, this is the familiar form of integral expression for creep that is used here. Now, we need to understand that this takes care of the superposition. We do not yet know whether for this arbitrary stress history scaling will work or not, and that is something that we need to do it based on the rules that we explained earlier as far as the scaling is concerned. Now, we are stuck here, we yet do not know what kind of form that one should use for j, because right now what we introduced, we have introduced j of t, we have introduced g of t also, we have also introduced j omega, we have also introduced g omega. So, what should be the structure for this? We need to spend some time thinking about it. So, let us do that first. Okay.